The last speaker of this afternoon's session is Hande Cingil, who will talk on conjugated polyelectrolytes as mechanochromic sensors for monitor supramolecular assemblies.
Good afternoon, everyone. Thank you for the introduction. Yeah, I have actually strictly 20 minutes to tell you about these mechanochromic sensors and how we designed them to use them to monitor supramolecular assemblies. But first, I would like to start why supramolecular systems are important for us. And many of you, we are also intrigued by the nature. And supramolecular systems are abundant in nature. Simply, we have been already listening lots of talks in this workshop where we try to make lipid bilayers and we try to make actually the best drug carriers. But to be able to do these, to progress in this field, we would like to understand how the interactions work actually. And these, all these highly ordered structures in nature are driven by supramolecular interactions, and they are far from being easy. So supramolecular interactions, we all know, they are non-covalent interactions. They are transient and they are dynamic. And we consider them as weak, but that is when they are alone. However, we know multiple of them cooperatively or sometimes competitively interact and play a role of defining the final structure. So what we had done to understand a little bit of these supramolecular interactions is we just opened a window and through which we would like to see the interactions while they are happening, non-invasively and without disturbing these systems. And to do so, we have designed these molecular mechanosensors, which I will show both of you here, but introduce you one by one. In the first one, you see the sensor one. This is actually a polyfluorine. And polyfluorines are actually nothing new. They are blue light emitting source. In the applications already we have a lot of those abundant. But if you look at this structure, it is an aromatic, very aromatic structure, and it is rigid and it is extremely hydrophobic. So we want to do electrostatic complexation with these polyfluorines, and it is not possible if they do not, of course, dissolve in aqueous conditions. We substituted the fluorine at the monomer level with alkyl tails, and they are functionalized with carboxylic groups. And above a certain pH, they are simply anionic polyelectrolytes. But how are they a sensor? Comes with the fluorescence emission spectrum of them. When you look at the top left graph, this is a polyfluorine. When it is in its regular phase, it is the polyfluorine emission spectrum. And for your convenience, I labeled the bands 1, 2, and 3, where you see the first band is actually the main emission band in the regular phase polyfluorine. And when I say a regular phase, I simply mean the schematic on top of that figure, which is sort of semi-rigid structure. They can never be flexible. They are semi-rigid in the good solvent already, so they still possess a bit of rotational degrees of freedom. But this conformation can be actually transformed into a fully stretched, planarized, and almost a frozen state. And that is in literature called as beta phase. And when the conformation changes into this new phase, it affects the photophysics of the molecule. So what happens is, it is still in the blue light regime, but electronic configuration changes. The first band completely disappears, and the second and third bands becomes the prominent emission bands of the system. So this transition can happen via many ways, but in our system, this transition only happens when let's say when a force is exerted on the backbone of polyfluorine. And with force, I don't mean we hammer these polymers, but a force which comes during the electrostatic complexation. But I will go into the detail in the following slides. And now I will introduce you the second sensor, which is simply the same as the first one, with a minor detail where we actually doped the backbone with an acceptor unit that is called benzothiazole, and it's actually a universal acceptor. So from fluorine to the BT, there is energy transfer. But we had designed it in a way that we have quite few of those in one chain, so we prevent intramolecular energy transfer, but we only have the energy transfer which comes when multiple chains comes closer. So the reason behind that is we want to use the second sensor to actually probe the proximities of the chains. So we want to know during the complexation studies, when multiple chains bundle, come together, we want to know this in its fluorescence signal. And what happens in the fluorescence signal, which is at the bottom right corner, when FRET happens, so when we have chain bundling in the system, we no longer have a blue emission, but the emission signal completely transferred to BT, and that is an orange-red color. So I will now going to tell you how we use them in multiple systems. And the first system is a protein polymer bottle brush-like system, in which we had actually used bioengineered polypeptides. And in the next one, we have a complex conservate core micellar system that is completely synthetic. All the constituents are synthetic. And later we have viromimetic capsid assembly, which is studied with these sensors. And there again, we have a bioengineered polypeptide. And I'm not going to talk about these in this order, but in a more, I think, understandable order. I will talk about them a little bit in details. But due to the time restriction, I am passing quite fast. So I hope it will still go through. In the first system, where we have the protein polymer bottle brush-like system structure in the end, we start with the first sensor, so homopolymer polyfluorine, which is anionic. And we slowly introduce the polypeptide into the system. And this polypeptide is a diblock of polypeptide. The green part is a collagen-inspired 400 amino acid unit zwitterionic and hydrophilic group. And this is simply responsible of the stability, and also it is responsible of the force that I was mentioning to you before, force that is exerted on the polyfluorine chain because of the steric repulsion. And the red part is consisted of 12 lysines, and that is positively charged, and simply that is to bind on the polyelectrolyte, anionic polyelectrolyte. And throughout this presentation, I mention mixing ratio instead of charge ratio. What I mean is a positive charge over the total number of charges. So when charge ratio is 1, actually in our case it is F plus 0.5. So if we start first how we utilize this sensor and what information we get in an electrostatic co-assembling system, the first thing is binding. So binding, I mean, yes, we have oppositely charged polyelectrolytes in the system, but we need to be sure that they are actually electrostatically binding. And it is very simple when you have a conjugated polymer in the system. Even small, very small number of opposite charge binds to the conjugated backbone, we see a tremendous fluorescence intensity change. So simply what happens is by increasing the mixing ratio, so adding more polypeptide into the system, we are simply quenching the fluorescence intensity which comes from the polyfluorine. So that is the number one confirmation of actually this system is complexing, and gradually it is binding on the conjugated polyelectrolyte. But a more striking information comes due to the fact that this polymer, as I told you, can transform from regular phase to a beta phase. But in this system, what we see is gradual binding on the backbone is actually causing a gradual transition from a regular phase to the beta phase. As you see here, this is not a fluorescence emission shift, but it is literally a complete new electronic configuration. Gradually, the first band disappears, and the second and third became the prominent emission bands. And this comes to a saturation when actually the charge ratio, charge stoichiometry is obtained. With this, we also move forward. So we claim this is electrostatic complexation, so then it should dissociate by addition of salt into the system. And one thing is, if this polymer can be used as a sensor, can it be also reversed when we add the salt? So can we actually recover, or if this is an irreversible process? But what we see, by addition of the salt, it really dissociates the complex, and when the polypeptide simply leaves the backbone of the polyfluorine, we recover the regular polyfluorine back into the solution. And with this, we had also done a bit more quantitative studies, which I am not going to go into detail, but what you can do is, if you know the characteristics of the constituents of this co-assembling system, you can actually determine the number of proteins bound on the conjugated backbone, and also the surface density, and even the amount of polypeptides leaving the backbone while salt is added. And from this, I will move to the next one, which is gonna be a good transition. That's why I put this in front of the other system. And in here, we have actually the same type of polypeptide. The only difference here is it is a bit more complicated due to the fact that there is a middle block where you see the as black, represented as black, and that's a cooperativity block. It is a silk-inspired block. A colleague of mine has simply designed this and produced to obtain viromimetic capsids. So I don't know the details of it in the bioengineering side, but what it does is simply it folds and stacks into stiff filamentous fibrils with beta roll structure. And he also successfully demonstrated the coating encapsulation of double-stranded DNA into virus-like particles. But the characterization that they could have done with this system was limited with AFM. So in the AFM, they put it in the system. They started, the system. So it simply nucleates, and it is told to be designed of a templated self-assembly. So it simply finds the DNA, it nucleates there, and it condenses and encapsulates it. But one thing they could not check if this could happen also in a non-templated manner. So if at high concentrations of this protein in solution, is it also still doing the capsid formation, but void, no template inside? So this is what they were actually concerned, and in this work, what we tried to do is actually finding out that. And how we did is very similar like the previous one, but this time we cannot actually interfere with the process because it is self-assembling by itself. So we start with a very low mixing ratio and a charge stoichiometry and an over the charge stoichiometry, so 3 cases. And we simply leave the system in fluorescence spectroscopy and we measure it for a very long time. And what you see is actually the time evolution of the fluorescence spectra of this conjugated polyelectrolyte during the encapsulation. In the low charge stoichiometry, you see the binding, which comes with the quenching of the signal, but as you see, there is no stretching. And in the charge stoichiometry, it binds, and it also manages to stretch the polymer. So it has enough protein in the solution to simply cause the force which is needed for the stretching. And over the charge stoichiometry, interestingly, it binds, it decorates the backbone. However, it is not stretching fully. So as you can imagine, this is our conjugated polyelectrolyte here is serving as a template instead of the DNA in their experiments. So we wanted to go further in detail of this. Why at over the charge stoichiometry, it is not stretching as much as the charge stoichiometry. And what we did, we just increased the concentration 10 times higher and repeated the same experiments. And what we observed eventually is the coating fraction, which is determined by the band 2 over the 1, is simply less when the concentration is higher. And this was actually, even if you look at the right bottom graph, when F plus is 0.70, it is simply encapsulating the polymer, but then leaving the template and going somewhere else. So where it is going is actually, obviously, there was a competition between templated versus non-templated assembly going on. And when the concentration is high enough, this protein is actually favoring to self-assemble by itself, not with the templates. And the last thing we had done on this very complicated system was trying to find out when this capsid formation happens, do we have single chain in the core or multiple chains that are actually going in? And we had the means to do this because we had the sensor too, which was detecting the proximities. When the many chains come together, we had to have FRET, so energy transfer. And when you look at the bottom graph, we had a bit of the FRET happening. I say a bit because in the next experiment, what I will show you is a complete transfer of the energy during the complex co-observation. So here we still conclude that chain bundling was happening within the capsid when the concentrations were high enough. And here the last example I'm gonna give you is completely synthetic system where we use the sensor too, so the proximity sensor with synthetic diblocko polymers. We have P2MVPs and PEO, where PEO serves as the hydrophilic group, and the P2MVP is quaternized, so it contains positive charges. We varied the block lengths, and but here I'm showing you just one example. What we see here very quickly is from the quenching of the fluorescence signal, we confirm the binding. From the changes of the bands, vibronic bands, we confirm the stretching. And from the energy transfer, we confirm the clustering. And what it means simply is we could confirm that for the complex co-surveyed core micelles to happen, we had a transition from single molecular complexes to multimolecular C3Ms by increasing the mixing ratio. And here, this is as the confirmation that this second sensor serves as dual sensor. On the top graph, you see the force sensing capability of it while increasing the mixing ratio. And at the bottom graph, you see that at high enough mixing ratio, the FRET happens. So simply the proximities increases and C3Ms form. And with this, I would like to conclude. I hope I have shown you that we opened a window through these different systems, and we tried to actually understand when the interactions were happening. But as you can imagine, this is a very young research. It's just 3 years old. And what we had done in those systems, it is just static systems. So we have pH controlled, temperature controlled, only we varied the concentrations and look into. So where this work goes is actually more autonomous and dynamic systems. For example, a current work is ongoing in the complex co-surveyed core micellar systems, but this time it is temporarily programmed to go through self-regulated transient pH states in which we use these sensors as a pH sensor instead of the conformations. So I want to acknowledge this work. A majority of the work has been done in Wageningen in the physical chemistry and soft matter group. And the last bit, which is going towards the dynamic systems, are now happening in self-organizing soft matter group in Eindhoven University of Technology. And I would like to thank everyone involved in this work, and also to you, and also to the funding. Thank you very much.
Thank you very much indeed. We have time for maybe one quick question. Yep.
Very nice talk. I wonder if you also measured emission lifetimes of your probes, and if you know how they change, if the conformation of the probe changes.
Yes, we actually wanted to do that, but we did not have the means to do that. We had done trial experiments, which didn't really go well. It can be done. I think it would be very nice to make a complete understanding of the whole system, but we haven't achieved so far.
Thank you.
Question?
No, not a question. I think that was the only question.
Sorry?
Was that the only question?
Oh, okay. You are the organizer.
Yeah. So no, I'm not asking a question. So I think we thank the speaker again.
Yes, okay. Thank you very much.